Hello and welcome back to our lab on architecture and networks. We will go to lab 3. We will concentrate into arithmetic for computers. This is outline of our lab today. We will have we will work with binary multiplication and binary division. Now I will give you the overview about what we will do in our first part of binary multiplication. Here you have this document, lab 3 no solution, and if you look into this, you can see we will go through an example of binary multiplication and make comparison with how we do it with multiplication in decimal. We will have hardware design for the multiplication, the basic hardware, and together with that basic hardware I will introduce about the algorithm. I think you should learn about this algorithm before at your lecture also, and then we will apply that algorithm to show multiplication, and here is an example of how the algorithm will work during a multiplication of two operands, and we will need to look into the value of each operand, multiplier and multiplicand, together it with the result in the product register step by step, and then you will need to do yourself for the exercise 1. We will apply the same algorithm, the same execution in multiplication, but we will have different values for multiplier and multiplicand. Of course, I will show this program together with you so that you can check the result yourself and understand how it works. And then we will have exercise 2, in which we will upgrade or we will refine our previous hardware design for multiplication to reduce the hardware used, and then you will need to apply that hardware into this multiplication with this initial value, and then you need to apply that hardware into this, and step by step, so that you can see how multiplicand and the product will change until you get the final result. Of course, I will work together with you with this also. Well, now I will come back to my slide for further explanation. So now we go to the first example of binary multiplication. Here is an example. If we have a number 8 for multiplicand and number 9 for multipliers in binary, we need to multiply them together, and the multiplication will work similar with that in decimal number. We will need to take this number 1 and this value 1 and multiply with this multiplicand and write it down here, and then we take the second value from the right, number 0, and multiply with this multiplicand and write it down here, but one bit further, shift further to the left, so it's located here, and then this value 0 will be multiplied with this 1000 and written down here, and finally this value 1 will be multiplied with this multiplicand and write down here one bit further to the left, and so it looks like this. And if we add them together by column, we will have the result written here. It will be 1001000, and it means 72 in decimal number. Now we will go into another exercise, your exercise, but I will explain it here. You should do it yourself also. So here is the multiplicand, number 2 in decimal. Multiplier is 3 in decimal, and the representation of these two numbers in binaries are 0010 for 2 and 0011 for number 3, and we need to know how can we multiply them together in binary. And here is the answer. At first you need to take this number 1 and multiply with multiplicand, which is 0010, and written down right here. So it is 0010, and then you take the second one here, you multiply with this and write down from here 1 bit further to the left, so it is 0010 written here. Next, this value 0 will be multiplied with this one, and the value, the result, will be written down here from here to the left. 0 multiplied with anything, it is 0, so we have 0 here. And finally, this 0 multiplied with this will be written from here further to the left. So we have all 0 here, and we add the column together for the final result. We will have 00001110, and it equal to 6 in decimal. Well, we can see that when we add the column like this, it means we fill the white area here by value 0. You can see if we add 0 here, here, and here, we will have 0 plus 0 plus 0 plus 0, and it is 0. Similarly, under here we fill by 0, and here we fill by one more 0, so it will be 1 plus 0 plus 0 plus 0, and it will be 1, and so we have the same value. So we can see from this that in fact when we add column together like this, it equal to we fill the white area here by 0 and adding by column together. Well, together we know that already, so we will go a little bit further about the algorithm for this multiplication. Well, now we start again by this value number 1, value 1 multiply with 0010. You can see it is 0010 and written right here at the most left, most right, and this value will equal to multiplicand multiply with 1, because the location of this bit is the first bit on the right, so it is multiply with 1, no shift left at all, and then it multiply with 1, that is this value itself. So this value 1 multiply with this, and then shift nothing, shift for 0, and we have this value. For the second bit of multiplier, this value 1, we will do the same, but at this time this value multiplicand, we need to shift 1 bit to the left and then multiply with 1. So you can see that we shift this value 1 bit to the left, it equal to this value multiply with 2 or shift left for 1 bit, and then multiply with this value number 1 here. Again, we fill this by 2 0, and so we have this value of 0 multiply with multiplicand, but this multiplicand must be shift left for 2 bits or equal to this multiplicand. Multiply with 4 and then multiply with the value 0 here. Similarly, for this value 0, we will have the multiplicand multiply with 8 or this multiplicand shift left for 3 bits before multiply with the value 0. This value 0 located here, and we add them all together. We have the same result of 6 in decimal here. And the question now is, should we do all this bits multiplicand and write down like this before we add them together to the product? We will answer it in the next slide. Here you can see that we don't need to do so. We can initialize the product by some by 0 and then right after each of multiplication in one line we will add them to the product. How can we do so? Here you can see it. When we multiply 2 and 3 together, we will initialize the product by 0. Right at the time we multiply this value, the first bit or bit 0 of multiplier together with the multiplicand, we have this temporary or immediate value 0, 0, 1, 0, and we will add this value together with the product right after, and so the product will change from 0, 0, 0, 0, 0 to 0, 0, 0, 0, 0, 1, 0. That is 0, 0, 1, 0 here added to the 4 bits of 0 here. For the next line in which the second bit of multiplier multiply with the multiplicand, we can see the result of this bit multiplication is this one, and then if we add this value immediately to the product, we can have this value of 1 will be located here. So the result is this, and we have the product is 6. After that, this value of 0 multiply with this multiplicand, and we have this 0 value, and if we add this 0 value together with the product doesn't change at all, and so we still have this value. And finally, for the last bit 3 in multiplier, the value of this bit is 0, and so when 0 multiply with this multiplicand, we have 0 located here, and if we add it together with the product, we still keep the product value of number 6. Well, so now we go to with those understanding, we go to the algorithm. So for the algorithm, you can see the algorithm shown here, but I will zoom it up so you can see it easier. We will start here, and at this time we will also initial our product by 0, and then we will test the first bit 0 of multiplier, whether that value is 0 or 1. If the value is 1, we know that we will need here, we come back here, we test this bit value. If it is 1, we have this value is the multiplicand, and so we need to add this value or the multiplicand value together with the product here, so you can see it. So here after we test this bit, if it is 1, we will add the multiplicand to the product and place the result in the product register, and then we will go down here. After doing so, we need to shift the multiplicand register left 1 bit. Why? You can see that after the first calculation, you will need to shift the multiplicand left to the left for 1 bit before you take this bit and multiply with this, so that you can have the second line, the result in the second line here. That's why we will need to shift the multiplicand register to the left for 1 bit. And together with that, we will need to shift the multiplier register to the right for 1 bit. Why do we need to do so? Because after the first calculation here, this bit is already used. We don't need to use it again anymore, but we change to this bit. So if we shift this value 1 bit to the right, this bit will located at the 0 location, or that at the bit 0, and so we will need to check the bit 0 only instead of check bit 1, 2 and 3. So we will shift the multiplier to the left for 1 bit, and then we check whether we already complete all the bit computation or not. If not, we will come back to our to this location, and we get again here to test the multiplier. If the multiplier is still 1, we will do the same. If the multiplier is 0, we know that when the multiplier bit 0 equal to 0, it means we will multiply the multiplicand with 0 before adding together with the product. So we don't need to do any addition here, but we will go straight to shift the multiplicand register to the left and shift multiplier register to the right before we check the number of loops or number of repetition to make sure that we already scan through all our bits in the multiplier. And after that, we will have the product, and we done here. So looking into this, this is the summary for this algorithm. You can see that you will need to initial the number of repetitions by the number of bits of the multiplier. For example, if you have 64 bits multiplication, you will need 64 repetition, and that's why here it is written down here by 64th repetition, and before you are done. So, and this is the simple hardware for that algorithm. You know that at every step we will need to shift our multiplicand 1 bit to the left, and then we add together with product here. Come back to the ALU, so the multiplicand will be added together with the value of product. And we also know that for the multipliers, in order to make sure that the bit that is in it, the bit that we are working with in the multipliers is always located at location 0 or bit 0, we will need to shift multiplier 1 bit to the right at every time. So multiplicand shift left for 1 bit, multiplier shift right for 1 bit, and then we check the value of the last bit 0 in multiplier to make sure if we need to add this multiplicand together with the product or not. If bit 0 of multiplier is 1, we will add the product together with the multiplicand and then shift multiplicand left again, and at the same time we shift the multiplier 1 bit to the right. If the bit 0 of multiplier is 0, we will do nothing with the product, but just shift the multiplicand 1 bit to the left and shift the multiplier 1 bit to the right. And of course here you can see that we will need to initial the value of product by value 0. Now we will go into our example in which we will look into the change of value inside multiplier, multiplicand and product. In our example, we assume that multiplier is 3, 0, 0, 1, 1 in binary. Multiplicand will be 2, ended by 0, 0, 1, 0 in binary. And we need to initial the value of product by 0 or 0, 0, 0, 0, 0, 0, 0, 0 in binary. At first, we check the bit. We check the bit 0 of or the most left, most right bit. The last significant bit of multiplier, the value is 1. So we know that we will need to add multiplicand together with product to have the new product value. So after checking this, we will add the product, that is 0, together with multiplicand, that is 0, 0, 1, 0 here, and we have the new value for product. And then we need to shift the value of multiplicand 1 bit further to the left. So you can see here we shift it 1 bit to the left, and the new value of multiplicand will be 0, 1, 0, 0 here instead of 0, 0, 1, 0. And of course at this time we just shift multiplicand, so no change in product and no change in multiplier. After that we will need to shift multiplier 1 bit to the right. So the value of multiplier here, shift 1 bit to the right, this value 1 will be lost and this value 1 will located at bit 0, and one more 0 will be pushed into the beginning or into the left of the multiplier. And so we have this value for new value for multiplier, and we will move to the step 2. At that time we need to check the most the last significant bits of multiplier or bit 0. This value is 1, so we need we know that we will need to add value of multiplicand together with value of the product, and so here we add them together, and the value of product will be changed from 0, 0, 1, 0 into, you can see here, adding 1 here together with this, so it create 1 here, so the new value will be 0, 1, 1, 0. We will do the same with multiplicand and multiplier. We shift multiplicand 1 bit to the right, to the left, shift multiplier 1 bit to the right, and we have these two new values. And at this time we know that bit 0 of the multiplier is 0, so we will not make any change to our product, so product keep its value, while the multiplicand we need to shift 1 bit further to the left. Multiplier shift one more bit further to the right, and in this case one more 0 will be added here, and this 0 will be removed, so the result is still 0 for multiplier. And again we know that this value, the value of bit 0 for multiplier is 0, and so we will make no change to the value of product, and so we have the product keep the same value, that is number 6 in decimal. And of course in this step 4, we will need to shift multiplicand one bit further to the left, and shift multiplier one bit further to the right. And here you can see that multiplier has 4 bits, and so after 4 iteration we will stop our operation, and we can get the result of 0 0 0 0 0 1 1 0, that is value 6 in decimal. Next is the exercise that you should do it yourself, in which you have this multiplier, this multiplicand, here is 9 and this is 8, and you have the initial value of product is 0. You need to apply this algorithm to give the value, the intermediate value for multiplier, multiplicand and product at each step. I will give you the answer here, because so you can understand it, or you can make reference with your answer to make sure you understand the situation and have the correct answer. So here is the initial value. We will do completely the same with our previous example, but with different value only. So we know here the less significant bit of multiplier is 1. We will need to add multiplicand together with product and then write it into the product. So the new value of product will be here 8 plus together with 0, or in other words it is 1 0 0 0 plus with 0 0 0 0, and so we have the value of 8 in product. Here 1 plus 0 will be 1 here. So the new value of product will be written here. Then the multiplicand we need to be we need to shift multiplicand one bit to the left, and so 1 0 is inserted after this bit, value 1 here shift to this location, and this value 0 will be removed, and the new value of multiplicand will be 0 0 0 1 0 0 0 0. No change in multiplier and product at this step. And then multiplier need to be shift one bit to the right, and so this value, this bit with value 1 will be removed, and so it will be 0 0 1 from the right, 0 0 1, and then one more 0 will be inserted into the left. And at that time we know that the less significant bit of multiplier now is 0, so we will not make no change to the product, and so product keep no change, but after that we will need to shift multiplicand this one bit further to the left, and we have new value here. Together with that we will need to shift multiplier one bit further to the right, and we have the new value here. and then we know that the less significant bit of multiplier is 0, so there will be no change in the value of product here. So we have value of product keeps the same, and then we need to shift multiplicand 1 bit further to the left, shift multiplier 1 bit further to the right, and we will have the less significant bit of multiplier now is 1. Here you can see, and so we know that if the value of multiplier of the less significant bit of multiplier is 1, we will need to add the multiplicand together with the product. So the new value of product will be this value plus with this, and you can see it will be 1 here plus with 0 here, so it will be 1 here. Here all other is 0, but here is 1, so 1 here plus with 0 here generate 1 here. So the new value of product will be 0 1 0 0 1 0 0 0, and then we shift multiplicand 1 bit further to the left, shift multiplier 1 bit further to the right, but at this time we already finished 4 iteration, and so it is equal with the number of bits for multiplier 4 bits, and so we know that our algorithm will finish here, and we have the final product here 0 1 0 0 1 0 0 0, and this value in binary should be 72 in decimal. Before going to our improved hardware, I will come back again to our exercise with some change in the way we make the multiplication, so that you can easily understand the improved in our hardware. So now we know the same bit before. We know that we will multiply bit to each bit of multiplier together with the multiplicand, and then we add with our product, which is initial by 0. But at this time, instead of shifting multiplicand 1 bit by 1 bit further to the left, we can see that if we shift instead of that, if we shift the product 1 bit to the right into some available space, the value will not change at all. So now we will do our multiplication. At first we will take this value 1 multiply with this multiplicand, and we have this value, and we will add this value together with our product and immediately shift the product 1 bit to the right. So here you will have 0 1 0 0. If you count from the right, you have 0 1 0 0 here. But instead of align the bits at this line, you align it 1 bit further to the right. It means you will shift the product 1 bit to the right into some available space. Please remember that in this case we should have some available space for the product on the right, otherwise this bit will be missing. And then for the next step, when we take this value, the second bit of multiplier, to multiply with multiplicand, here instead of shifting multiplicand 1 bit to the left, we keep it at the same location, and so we will have the value 0 0 1 0. And as you can see here, due to our shift of the product 1 bit further to the right, this bit, if these 4 bits, if adding together with product at the same column, we will have value 6. So we add this together, this bit, these 4 bits, adding with this bit until this line, and so we will have value 6. You can see here 1 will located here, this row 1 will be located here, and then we shift the product 1 bit to the right. So here we will have the product look like this, and again the value 0 in the third bit of the multiplier. When multiply with the multiplicand, we have value 0 here and value 0 here, adding together with this. It makes no change into the product, but we will shift the product 1 bit further to the right, and so we have new value this. Again, the last bit of the multiplier, bit 3, where when multiply with the multiplicand, as this bit is 0, we will have the value of 0 located here, and then 0 adding together with this. It makes no change into the product, but the product will need to shift 1 bit further to the right. Yeah, so you can see here, when we shift the product 1 bit further to the right, we have this value. So if we align the data from this location, bit 0, 1, 2, 3, 4, 5, 6, 7, you will have the same value of product with the one you have before, that is 0, 0, 0, 0, 1, 1, 0. And so what is the advantage of this kind of multiplication, so that we can improve our hardware? You can see here our product will initial at it will be initialized at the high part of the product register. The lower part will leave unused, and then we will shift gradually shift that to the right. Together the multiplier will be shift left, will be shift to the right also. So at the initial time we can definitely use the higher part for the product initial value, and the multiplier can be written into the lower part of our product. And one more thing is we don't need to shift our multiplicand, so we can keep our multiplicand the same. And so here is the upgrade of the multiplication hardware. As I told before, our product register here will be divided into 2 parts. The left side is the is used as the or the initial for the product, while the right hand side will be used for the multiplier. And so this half will be used as the product added together with the multiplicand, and then it will shift to the right. At the same time, the value of multiplier here we need to shift to the right also, and so it makes no change in the in our algorithm. The least significant bits of multiplier will always be stay here, while the bits that already been used will be removed out of our register. Well, if we make comparison with our previous version of multiplier here, you can see that in order to do 64 bits multiplication, we need only 64 bits for multiplicand and 120 bits, 28 bits for the product and the multiplier. So in total you will need 192 bits in total. But for this version, the first version, you need 64 bits. Here please remember that in this case it is a 32 bits multiplier, and so if you want to make it 64 bits multiplier, you will need to double all these value. And here you can see that we need 64 bits of multiplicand, 64 bits of product, and 32 bits of multiplier. And if we double all these value, we will have 1 time of 32, 2 times, and so 3 times of 32, and 5 times of 32. Double them, it is 10 times of 32 bits, and so it is 320 bits together to show the same problem, in which this hardware can show that problem with 192 bits only. And so now here is the summarize about the upgrade multiplication hardware. In our upgraded multiplication hardware, the optimization comes from the reduction in the number of bits required for doing the multiplication. And in our hardware, the multiplier and the product are shipped while the multiplicand is added to the product if the multiplier bit 0 or less significant bit is 1. Well, next we will move to our exercise using this hardware, using the refined multiplication hardware. And here is the question for our exercise. In binary multiplication using the refined hardware, we have the initial value of MD or multiplicand is 0, 0, 0, 0, 1, 0, 0, 0 or 8. And we have the initial value for product, the higher part, the left part of the product P is 0 as initial value. The lower part, the least significant 8 bits will be initial by the value of multiplier MR, which is 0, 0, 0, 0, 1, 0, 0, 1, and it is value 9 in decimal. We will need to find the value of multiplicand and the value of product, include the first the left part and the right part of product for each step in our execution. So in order to make it clearer, I will make a dim letter together with a dim line here to separate between the high 8-bit parts, or the most significant 8 bits of the product, and the lower part, the less significant 8-bit for the multiplier. So as we can see here, the initial value for MD is 8 in decimal, and the initial value for P or product is 9 in lower bits for or 1001 for multiplier. As we can see here, the least significant bits of product or the least significant bits of multiplier here is 1, and so we know it is 1. So we know that the high part or the most significant 8 bits part of the product need to be added together with MD before shifting all the result 1 bit to the right. So we add this 0 value together with MD here, and so you can see one look available here. So when added, one will be available here, but after adding together we need to shift all the regions in P one bit right, and so the bit here will be, the bit 1 here will be located here. This bit 1 will be removed and this bit 0 will be shifted to this location, and so we have the new value of register P here, in which the result for the product should start from here up to here, and the remaining for the multiplier will be started from here to the right until here. And after this step, we can see that so here we see this value is 1, and so here we will multiply MD with 1 before shift, before adding and shift to the left. And now at this line you can see here we have the value of 0, so we will do MD multiply with 0 and added together with P before shifting to the right. So here you can see that here is 0, so we multiply MD with 0 and we added it with P before shifting all this to the left, added it with the higher part of P before shift all to the right for 1 bit. So here you can see the value here will be unchanged, but it shifts 1 bit to the right, and so bit 1 here will be moved to here. This bit 0 will be dismissed, and this bit 1 will move here. So the value of product should start from here to the left, and the remaining of the MR should start from here to the right. And again we can see that we have value 0 here, so the next step we will multiply MD with 0 plus with the higher part of or the most significant 8 bit of product, and then shift the result to the right for 1 more bit. So the result, this value when shift to the right 1 bit, it will change into this result. And here we can see that we have the value 1 located at the end here. It means that the less significant bit of multiplier now is 1. So in that case we need to multiply this 1 together with MD before adding together with the most significant 8 bits of P of products, and then shift all the product to the right for 1 more bit. So you can see that if you add this value together with this value, this value 1 here will be added here, and we will have 1 here, but we need to shift everything to the right for 1 bit. So this bit will be shifted to the right and located here. Similarly, this bit 1 will be located here. And here we get to the 4th step. So value of so MR should be start from here to here, and value of product should start from here to here. Again, here we have value 0, and so MD will be multiplied with 0 and plus with the higher part or the most significant 8 bit part of products, and of course MD multiplied with 0, it means 0 and P will or the most significant part of P will keep unchanged, but will be shifted to the right only, and here is the new value in the 5th step. After that here is 0, and similarly we will do nothing change for P, but just shift it 1 bit to the right, and so we have the new value here. And again 0 is available here, and so we will shift P to the right one more time, and we have this value, and as you can see here, the last bit or the last MR, the last bit in MR will be 0, and so P will be shift again one more time to the right. And at this time we already do for 8 times. It is equal with the number of bits for multiplier, in this case 8 bits for multiplier, and so we will have this as the final values of our multiplication between 8 multiplied with 9, and this value is 72. Of course we can check it by our calculator in programming mode. So here is 0 1 0 0 1 0 0 0 0 1 0 0 and then 1 0 0 0. So here you can see in decimal the result is 72. It is equal with 8 by 9. Next we will go into our second part in binary division. We will look into our part 2. Here we will have an example of how the binary division will work with this example, and then we will look through the hardware, the basic hardware for a division, together with the algorithm following this hardware. You already learned this at your class, and then we will look into an example. We will have a divisor together with a remainder. We will look into the detail step by step how the divisor change, how the divisor and how the remainder change their value following this algorithm to make the final result for the question. And then we will go into our exercise. The first exercise will be given with some divider together with remainder, and then you will need to do yourself step by step to see how the divisor and how the remainder change their value until you get the final result in question. In exercise 2, the hardware will be upgraded or hardware will be improved. This basic hardware will be improved to reduce the hardware size, and then you will be given another exercise in which the divisor and the remainder will be given here, and you will need to do step by step to see how the divisor and remainder change their value until you get the final result. Now I will go into the detail by coming back to my slide. Here we have an example how the binary division work. It will work similar with the division in decimal. For example, we have a division n 100 1000 and a divisor 1000. This is 72 by divide for 8. So we will do the same with what we did with decimal number. We will have that the first 4 bits, the most significant 4 bits is bigger than the of the remainder. Here it is bigger than the value of divisor, and so we will have the result. The first bit result in the question is 1, and we take the most significant 4 bits of the remainder we subtract with the divisor, and the result here we have value 1 in this 4 bits at this bit, and then we will take down this bit 0 here, and the remaining here is still smaller than the divisor, and so you will need to add 1 0 here as the result in the question. Another 0 will be taken down here, and it is still smaller than the value in divisor, and so another 0 here. The final 0 here will be taken down here, and this value as big as the divisor, and so the result for this division will be 1 in the last bit in the question. And then you take this value and subtract with the divisor, and here you have the 0 as the remainder. And if we check for the result in decimal, you can see that this is 72, and it divides for 8, and the result will be 9 in this question. Our next example is this division. We take the same value 72 or 1001000 in binary, and we divide for 9, or in binary it is 1001, and we do the same. We can see that here we take divisor, and we put it at the most left in comparison with the remainder here, and we will take this part of the remainder, subtract to the divisor, and we can see the result here is 0. It means that this value of remainder is bigger or equal with the value of the divisor, and so the result in question will be 1. And then you can see that we will shift this value 1 bit further to the right. 1001, we shift further 1 bit to the right, together with using this value of the remainder. It means that the divisor will be shift 1 bit here. It will be 1001 located at this location, and we do subtraction with this remainder, and you can see that this remainder is smaller than this value, so we have value 0 here in the question. We do again, we shift this divisor 1 bit further, and we take out this bit 0 here, and we can see that the remainder is smaller than the divisor, and so another 0 here for the question. We do the same with the last bit 0 of the remainder, and we will have the question here 1000, and that value is 8 in decimal. If we look into that, we can see that at each step we will shift the divisor here 1 bit further to the right, and with that shifting we will automatically able to use the next bit of the remainder for the subtraction, this and then this, to subtract when this value or the divisor shift to the right, and so we can build an algorithm. Here is the algorithm. I will zoom it up now. You will subtract the divisor register from the remainder register, and place the result in the remainder register, and then you will need to test the remainder value. If the remainder larger than 0, it means that the result for that step will be 1 in the equation, and so it will shift the equation register to the left and setting the last bit, the less significant bit of the equation to 1, and then of course it will shift the divisor register to the right 1 bit, and then if you are not yet finished the execution for all the bits, you will need to come back to the next step, and at the next step you do the same. You will subtract the divisor register from the remainder and store the result into the remainder, and then you check whether the remainder is larger than 0 or not. If it is not, it means that you have to reverse the remainder back to the previous result, the previous value, and the result for the equation will be 0 for that bit, and so you need to restore the original value of the remainder by adding back it together with the divisor, and place the result, the sum result, in the remainder register, and you will need to shift the equation 1 bit further to the left while setting the less significant bits to 0, and you will go to the next step of shifting the divisor register to the right, and you need to check the number of repetition. If it gets to the number of bits you expect, you will need to exit or the execution has done. In this case, we do work with 64 bits data, and so here you have 65th repetition complete or not. And here is the summarize of the algorithm for division. This number of repetition will equal to the number of bits of the divisor plus with 1. Why we need to plus with 1? I think you already know at your class that the sign bit, and it means that, for example, if you want to make a division with the divisor of 64 bits, you will need 65 repetition to complete this work. And this is the hardware for that algorithm. You have the divisor, and you know that the divisor will need to shift right 1 by 1 for each step. So here you have shift right for divisor. You will need to add the divisor together with the remainder, add or subtract the remainder together with the divisor after shifting. So we have an ALU here to make the addition or the subtraction between these two values. The question available in this register when the result in the remainder is when the result of this subtraction is bigger than 0, you will have one put into this side of the equation, and then you shift the equation to the left. If the result of this subtraction is smaller than 0, you will put 0 here and shift the equation to the left as we do in the algorithm. And of course here you didn't see the divide n because the divide n, it can be considered as the remainder at the initial time. So the remainder here will be initialized by the divide n inside this. Now we will go into our example on binary division. We will see how Q or question dr or divisor, and r the remainder change during the calculation step by step. Here is the initial value of q, dr, and r. As you can see here, dr is 8 in decimal 1000. However, if you look into this, you can see that the most significant bit of dr here is 1. It implies that this is a negative number, so it is not 8. In order to make sure it is 8 in binary, we need to add one more bit here to make it 0, 1, 0, 0, 0, so it will be 8 in decimal. It will make no change to our hardware because in fact in our hardware we have 64 bit for dr, or at least we should have 8 bit for dr, and so we can add many more 0 in front of this. But for simplification, I will add only one more bit here. So here I give a note, one more bit 4 equals 0 for dr must be included into dr to avoid negative number, and when dr one more bit added here, of course you need to add one more bit here to make the left part, the length of the left part for dr is the same with the length of the right part for dr, and so one more bit here and one more bit here for dr. You can see that here dr is 5 bits, and so r must be 10 bits, double size of dr, and so 2 more 0, 0 must be added here. And we also have q need to be the same size with dr, and so one more bit 0 must be added here for q. And now we go to the first step. We take this r minus dr, and so you have this value 1 1 0 1 0 0 1 0 0 0. And if you look into this, you can see that this most significant bit of the result for r is 1. It implies that r is smaller than dr, and so the result is a negative result value, and so we must revert r back to the previous value by adding r with dr, and so we have the previous value returned here. For q, we can see that r is smaller than 0 here, and so q must be shift one bit to the right with 0 added to the most less significant bits, so one more 0 is here and shift to the right, so q didn't change its value. And then dr must be shift for one bit to the right, so you can have now instead of 0 1 for these 2 bits, it will be 0 0, and this 1 bit 1 here shift one bit to the right, and so it located here. Other bit will be 0 0 0 all 0, and value of r doesn't change at all. And then we move to the second step, which is initial by taking this value of r and minus to this value of dr. You can see that if we take the minus of this for this, we will have 1 1 1 1 0 0 1 0 0 0, and this bit, most significant bit here, which is equal to 1, implies that r is smaller than dr, or the result is a negative value. And so if r is smaller than 0 or negative value, we must revert r back to previous value, so we add r with dr and it changed back to the previous value of this. At the same time, we need to make change to q, and as r is smaller than 0, one more bit 0 must be shifted to the right of Q, and Q didn't change its value because it still be 0 0 0 0. And then DR must be shifted one more bit to the right, making this bit from here, bit 1 here will shift to here, and so we have 0 0 0 1 0 0 0 0 0 0, and this previous 0 bit will move out of our register. Why? Our R didn't change its value, so it is still here. Moving to the third step, we take R minus DR. We can see that here R is larger than DR, so the minus return this value 0 0 0 0 0 0 1 0 0 0, and this bit 0, most significant bit of R here, implies that this is a positive value, or R is bigger than DR here, and so we don't need to revert R back to previous value, and we move to changing the value of Q. Here R is larger than 0, so Q will be replaced by itself shift to the left, but the less significant bit will be 1. So 1 is added here to the less significant bit of Q, while all other bits shift 1 to the left, making Q equal 0 0 0 0 1 now. And then we must shift DR 1 bit to the right, making DR change to 0 0 0 0 1 0 0 0 0 0, and R is still the same. Now we move to the fourth step, in which we will need to take this R and minus to this DR. What you can see here is R is smaller than DR, so of course the minus value will be a negative value, and it is 1 1 1 1 1 0 1 0 0 0, and this bit, the most significant bit is 1, implies that this is a negative value, or R is smaller than 0, so we must revert R to the previous value by adding it back with DR here. So the value of R return back to 0 0 0 0 0 0 1 0 0 0, and Q, as we can see that R here is smaller than 0, so Q will be shift left 1 bit to the left with 0 push at the right, so it changed to 0 0 0 1 0. This bit 1 here shift 1 bit to the right, making this 1, and 1 more 0 is pushed into the right. DR and R won't change their value, and then we need to shift DR 1 bit to the right, so we change this bit 1 here, change to here, so the value is 0 0 0 0 0 1, and the remaining is 0, the remaining one are 0 0 0 0. And now the fifth step, we take this this R and minus to DR, and we have the result of 1 1 1 1 1 1 1 0 0 0. This bit value, most significant bit is 1, implies that R is smaller than 0, so we need to revert R to previous value by adding it with DR here, and we need to change Q value by shift itself to the right, to the left with 0 push to the right, so it value change to 0 0 1 0 0, and then DR must be shift 1 bit to the right, So this bit 1 here move here, so it changed to 0 0 0 0 0 0 and then 1 0 0 0. Now the sixth step or the final iteration, because we have 5 bits for DR, so we have 6 steps or 6 iterations in total. And in the 6th iteration, we will take value of R here and minus to DR. You can see that these two values are the same, so the result will be 0 0 0 0 0 for R, and this 0 implies that R is larger than or equal to 0, and so Q we don't need to revert R back to the previous value. Instead we will shift Q 1 bit to the left with value 1 pushed to into the right, and so value of Q change to 0 1 0 0 and 1, because this is a newly added 1 and it pushed to the right of Q, and then DR shifts 1 bit to the right, making and it changed to 0 0 0 0 0 0 0 1 0 0. And here we already get to the 6th iteration, and it is the end of the algorithm, and so the final result in Q will be 0 1 0 0 1. The remainder is all 0, so we can see that the result is 9 in decimal. The remainder is our exercise. We will apply the same algorithm into this value of divisor 1001, and the remainder, that is 0 1 0 0 1 0 0 0. So in this equation, in this division, it will need to take 72 divide for 9, and as we said before, we have this value 0 here. It is because we push the DR to the left, and so we have room to shift it to the right. That's why we have this 0 located here. You should do this example exercise by yourself, but I will give you the result here also, so you can make a comparison with it when you finish your work. Now we go to our exercise. In our exercise, we will have the same thing with the example, but instead of DR equal to 1 0 0 0, it is 1 0 0 1. In other words, R is 72 divided to 9 here. And similar with our example, we can see that DR should be a positive number, and so we need to add 0, one more 0 in front of DR and one more 0 in the middle of DR, making the left part and the right part of DR, the length of the left part and the right part of DR change to 5 bits, and totally DR is 10 bits here. Q will be 5 bits also, and for R, 2 more 0 must be added to the left, making R being 10 bits. And we do the same with our exercise. With our example, we take R and minus for DR. So here you can see that R is smaller than DR, and so the result of the subtraction will be 1 1 0 0 1 0 1 0 0 0. And this bit 1, the most significant bit here, equal 1, it implies that R is smaller than 0, and so R must be reverted back to the previous region, that is R will be added with dr and return back to previous value of R. At the same time, as that subtraction is smaller than 0, we need to shift 1 bit equal 0 bit to the to the less significant bits of Q, and Q didn't change its value at all, and it is still 0 0 0 0 0. And then we shift dr 1 bit to the right. As dr shift 1 bit to the right, you can see that bit 1, this bit 1 here shift 1 bit to the right, it changed to here. This bit 1 here shift to the right will be here, and so dr will be 0 0 1 0 0 1 0 0 0 0. And then to the second step, we will take R here and minus 2dr here. So as you can see here, R is smaller than dr, so the result will be a negative value, that is 1 1 1 0 1 1 1 0 0 0. And when we check the most significant bits of the result, it is 1, so R is smaller than 0. We need to reverse R back to the previous value by adding R with dr. So here the previous value appear here. At the same time, we need to push one more 0 bit to the right hand side of Q, shifting all Q 1 bit to the left, and Q still keeps the same value of 0 0 0 0 0. And we shift dr 1 bit to the right, and so dr change into 0 0 0 1 0 0 1 0 0 0. And now we move to the third step. Here you can see the R minus dr will be 0 0 0 0 0 0 0 0 0 0 0. And this bit equal to 0, the most significant bit of the result stored in R equal to 0, implies that R is larger than or equal to 0, and so we don't need to reverse R back to previous value, but instead we just push a value of 1 into the right hand side of Q, and so all Q will be shifted 1 bit to the left and change from 0 0 0 0 0 into 0 0 0 0 1. And then at the next step in this third iteration, dr must be shift 1 bit to the right, and it changed to 0 0 0 0 1 0 0 1 0 0. And then we move to the fourth step. You can see here R now is 0 and dr is larger than 0, so of course the result will be a negative value 1 1 1 1 0 1 1 1 0 0. And so here, as the most significant bit of the result is 1, we need to reverse R to previous value by adding it with dr, and the R will come back to 0 here. And then as R is smaller than 0, Q will be changed by pushing a value of 0 into the right hand side of the Q, making all bit of Q shift 1 bit to the left, and so the value of Q change from 0 0 0 0 1 into 0 0 0 1 0. So new bit 0 here will be pushed to the Q. And then dr must be shift 1 bit to the right, and it changed to 0 0 0 0 0 1 0 0 1 0. And then we move to the fifth step. the fifth iteration, we take R here and minus dr here, and this is the result of R minus dr. You can see that the most significant bit of the result is 1, so it implies that R is smaller than 0, and we need to inverse R back to previous value, and so here we have R return back to 0, and we know that R is smaller than 0 by this bit, so Q will be changed by pushing one bit with the value of 0 to the right hand side, shifting QO one bit to the left, so that Q will be 0 0 1 0 0 now, and then dr must be shift one bit to the right, and it changed to 0 0 0 0 0 0, and then 1 0 0 1 here, bit 1 here shift to here, and bit 1 here shift to here. And next, the sixth iteration, or the last one, similar with the previous one, we know that we have 5 bits of Q and 5 bits of dr, and so we need 6 iterations. And so we do the same. We take R here and minus for dr. The result is 1 1 1 1 1 1 0 1 1 1. So this is a negative value, or R is smaller than 0, and so we will need to reverse it back to the previous value. I forget to write that line here, but here we already revert it back to previous value, and we need to shift Q one bit to the left with the least significant bit replaced by 0, and so R will be 0 1 0 0 0, and so here and then dr must shift one bit to the right, and it changed from 0 0 0 0 0 0 1 0 0 1 into 0 0 0 0 0 0 0 1 0 0, and here is the last iteration. So the result available in Q here 0 1 0 0 0, it is 8 in decimal. The remainder is 0 also, and so we have here 72 divide to 9 equal to 8. Here our hardware to make it smaller. In order to know how can we upgrade our hardware, we will come back a little bit to our multiplication to see how the data work. In this slide before, we know that in order to make multiplication, we need the multiplier stay here, and then shift one bit by one bit further to the left. But instead of that, we can make the product gradually shift one bit by one bit to the right, and the result are the same. Here you can see the first result of multiplier of multiplication with this multiplier. It sits here. Instead of shifting it to the left, we shift the product to the right, and the next multiplier, the next result of this bit in multiplier multiply with the multiplicand, the location, instead of shift one bit further to the left, it sits right here, and the result will be written to product, but the product we need to shift one bit to the right, and we do the same, and finally we have the correct result, no change in our result. It means that instead of shifting a data in this multiplier to the left, we will shift the result to the right, and we will apply the same understanding to our hardware for division. Here, for example, so we know that we need at each time the divisor we located from here, and at each time, at each step, it will need to shift one bit further to the right, and the equation will appear, and the remainder keeps the same location like this. So the remainder keeps the same location here. So instead of that, we can consider like this. We don't shift this divisor to the right, but we keep it stable, and we shift the remainder one bit further to the left, and we will have the same value, the same result at the end. And if you look into the hardware by that manner, you can see that remainder shifts to the left, the equation also shifts to the left, and so we can take one bit by the equation and replace for one bit of the remainder at the end, and so finally at last we will have the remainder replaced for the unused bit in the at last. At the final step, we will have the equation replaced for the unused bit of the inside the remainder, and so here will be our upgraded hardware for division. Well, we have the remainder located here. The division will not shift at all. Instead, after each step, the remainder here will shift one bit to the left. The equation, one bit equation, the one bit equation result will be shift to the most significant bit of this remainder, and finally we will have 64 bits equation located in the lower part, or less significant 64 bit of this remainder register. We will go into the summaries of that hardware. The optimization comes from the reduction in the number of registers. So in here you can see that the remainder and the equations register are combined together, and they use the same register. The equation will gradually replace the unused part of the remainder. Shifting the we need to shift the remainder and the equation simultaneously with the subtraction of between the remainder and the division and the divisor. And so here we will have an exercise. We have an initial value for the divisor, the initial value for the divide n or the remainder, and you need to do yourself. You need to do this exercise yourself. You need to find the intermediate value for dr or divisor, r or remainder at each step, and finally you will have the final result of equation in our in this part, in the half part of the register r. Of course you should do it yourself, and after that you can come back with this video, because I will give you the solution step by step now, and you can make a comparison between your work and this one to find the to understand the hardware. So now and now we will show this exercise for the upgraded division, hardware for division. So here dr is 9 in decimal, or 1001 in binary, the R here will be 72 or 0 1 0 0 1 0 0 0 in binary. In order to make you easily seeing how it works, the value of Q will be shown by blue from now on here. As we know that, as we know before, we will work with a positive value of R and DR. And so here we can see that DR here, if we just use 4 bits for DR, it is this most significant bit equal to 1 implies that it is a negative value in binary. So we need to add one more bit of 0 here, making DR a positive value 9 in binary. And as we add one more bit here, we will need to add 2 more bits into R, making R to be 10 bits, double the size of DR, which is 5 bits now. Now the first step, we take the most significant 5 bits of R and we minus for DR. So the result will be 1 1 0 0 1. 1 here, the most significant bit of the result implies that R, the 5 most significant bits of R is smaller than DR, and so we need to reverse this red value back to the previous value by adding it with DR, and then for the Q or for the equation, the value will the newly generated value for Q will be 0, and that 0 must be pushed to the right of R, and so the new value of R will be 0 0 1 0 0 1 0 0 0 0, and this bit 0 here is belong to Q, and the remaining here are the previous value of R, but shift 1 bit to the left. Then we move to step 2. We take the most significant 5 bits of R here, which is 0 0 1 0 0 1. No, I'm sorry, which is 0 0 1 0 0, and we minus for DR, which is 0 1 0 0 1, and so it is the result is 1 1 0 1 1. Here 5 bits in red. This most significant bit equal to 1 implies that we need to reverse R, the red here, back to previous value by adding with DR, and then we for the Q, the result, the newly added bit for Q will be 0, and so 0 will be pushed here and making 2 bit for Q here, from here to here in blue, and the previous of R here will be shift 1 bit to the left, making it 0 1 0 0 1, and then 0 0 0 0 0. To the third step, here you can see that the most significant bit of R, which is 0 1 0 0 1, equal to DR here 0 1 0 0 1, and so if we subtract them together, we will have the value of 0 here. This bit is 0, and so we don't need to revert R back. Instead we just shift it 1 bit to the left together with pushing a bit of 1 to the right of R as the result of Q at this time, so making the value of Q to 0 0 1, and the full value of R here will be 0 0 0 0 0 0 0 0 0 1. And then for the fourth step, the most significant 5 bits of R here, when minus 2DR, it is a negative value, this one 1 0 1 1 1, and here this bit is 1, the most significant bit is 1, and so we need to reverse R back to previous value together with shifting it 1 bit to the left. And for the Q, for value of Q, this bit of 0 will be pushed to the right. And so R now 0 0 0 0 0 0 0 0 1 0, in which these 4 bits 0 0 1 0 are the current value of Q. And then to the fifth step, we take the most significant bits, 5 bits of R, which are all 0 here. We minus for DR. The result is 1 0 1 1 1, and this most significant bit is 0, and so we need to reverse R back to previous value, which are all 0 here, and we need to shift it 1 bit to the left by pushing 1 bit of 0 to the right of R as the result of current Q. And so the new value of Q will be 0 0 1 0 0. And then we move to the last iteration, iteration 6. And so we do the same. We take the most significant bits, 5 bits here, minus for DR, and here is the result 1 0 1 1 1. And as this bit is 1, the most significant bit is 1, we will need to revert R back to previous value and shift everything to the left by pushing 1 more bit of 0 into the right. So the new value will be 0 0 0 0 0 0 1 0 0 0, in which these 5 bits will be the final result of Q, which is 0 1 0 0 0, and it is 8 in decimal. And here is iteration 6, so it is also the final iteration because DR is 5 bits. So we have 6 iterations, and that is the end of our lab today. Thank you very much, and if you have any question, please send me by your email.